Hello, thank you for always watching. For those who regularly check my contents, it may feel like a sudden start of a lecture on recurrent neural networks. Usually, I upload the lectures in order, but I've started Q&A sessions to answer questions and requests from my audiences. Recently, I received a comment requesting an explanation of recurrent neural networks for beginners, so I created this video. This video is designed for beginners, but some foundational knowledge of deep learning may promote your understanding. So you can find the basics of deep learning in my playlist titled Data Science for Everyone. If you have not checked it, please check it out first. I could summarize this video shortly in one session, but it seems better to explain it in some detail, so I will upload it in several videos. I have also received a request for Python code. I plan to upload videos covering theory and Python tutorials as a part of machine learning lectures I am recently posting. If you have specific requests, please let me know in the comments. Feel free to leave a comment for anyone else who has requests. I will do my best to accommodate your needs if I can answer with my expertise. However, please be generous for taking time because I am creating these videos on my own, so it may take some time to produce these videos. So much for a preamble. Let's visit the world of recurrent neural networks. Session 1. What is recurrent neural networks? In this session, I will explain what recurrent neural network is and its structure. Sometimes we need to consider past trends in making a prediction. For example, if we want to predict a company's tomorrow stock price, we need to consider not only today's price but also longer past trends. And suppose we want to develop an automatic input tool that inputs sentences automatically by predicting the following words and phrases. In this case, if the sentence prediction is based only on the previous word, the prediction accuracy will be poor, and the tool will be useless. The prediction should be based on the past several words and phrases that constitute a context. An ordinary neural network cannot deal with such analysis that need to consider longitudinal trends. In this kind of analysis, recurrent neural networks will be effective. It is called RNN for short. RNN is a neural network that has a recursive structure. The word recursive means that a thing's definition or description contains the thing itself. The recursive structure of an RNN enables the network to handle longitudinal data. Longitudinal data is data that records the variables over a period of time. Stock price data that records daily stock price data over a period of time is an example of longitudinal data. Another example is time-lagged data, often used in psychological research, where dependent variables are measured several months after collecting independent variables. In predictive analytics with longitudinal data, the machine learning model makes a prediction using a sequence of data collected over a period of time. Let's consider a case where we collect the employee's data on motivation level as an independent variable. If the data is not longitudinal, the independent variable represents each employee's motivation at a specific time. In longitudinal data, an independent variable is a sequence. So, in this example, the independent variable should be employee's motivation, measured over time, such as several days, several weeks, and so on. RNN can be an effective predictor when we analyze longitudinal data, that contains sequences of variables. RNN predicts future values by finding some regularities or patterns in the variation of sequenced variables. As for language data, the meaning of a sentence is formed by the context of multiple words. So, if we regard each word as a variable, language data can be regarded as sequenced data with some regularities and patterns in the variation of variables. Thus, RNNs are widely used in language data analysis, such as automatic translation and speech recognition. In a longitudinal analysis, the model needs to see the data as a sequence. For example, stock prices are influenced not only by the previous day's price, but also by the variation in the prices over a certain period of the past. So, if the previous day's price is $100, the predicted price will differ depending on whether the price has increased to $100 or has decreased to that price. As for language data, the meaning of a sentence varies depending on the word order. It also depends on what words are used previously. So, a neural network needs to retain the past state within a network to make predictions based on the sequence of data collected over time. Recurrent neural networks can make such predictions by memorizing past states within the network. So, how do RNNs memorize past states? The basic structure of an RNN is similar with that of an ordinary artificial neural network. It is an ordered structure consisting of an input layer, hidden layers, and an output layer. In the following, we use the lowercase letter t as a sign to represent time. So, we express t as a time point and t minus 1 as the previous time point. For example, in daily data, if we write today as t, yesterday is t minus 1, and tomorrow is t plus 1. To retain the past state, RNN retains not only the value of the input data at the time point of t, but also the value of the hidden layer at t minus 1 as the input to the hidden layer at t. And then, the RNN transfers ht minus 1 to ht, the hidden layer at time t. The state at t will be retained. After that, at the time point of t plus 1, the state at t will be transferred to the hidden layer at t plus 1 as the state at t. In this way, all the past states are retained in the past hidden layers. Then, the retained state will be reflected in the present, recurrently. Let's visualize the bigger picture of RNN. X1 is the input data at time 1. The first data in longitudinal data does not have a past state. So, the input to the first hidden layer is only the first data. So, the first layer of an RNN receives X1 as the input. The hidden layer, H1, retains the state at time 1. Then, at the next time point, time 2, the input data, X2, will be input to the hidden layer, H2. In RNN, the hidden layer is called RNN cell. RNN cells are networks with the same structure that appear recurrently in RNN. Then, the previous hidden layer, H1, is also input to the RNN cell. That is, not only the current information, X2, but also the past information, H1, will be input to the second RNN cell. In this way, an RNN retains both the past information and the present information. The same process will be repeated until the time point t. The number of repetitions equals the size of the input data. So, when we input data with a size of 3, the process will be repeated 3 times. When we input data with a size of 4, the process will be repeated 4 times. For instance, when we use daily data and input data of yesterday, today, and tomorrow, the input data size is 3. When we use language data, the number of words included in the sentence is the data size. For example, the sentence, "We enjoy studying deep learning," consists of 5 words. So, its data size is 5. As we have seen, the output of an RNN layer will be determined by the new information xt and the hidden layer ht-1, which records the past information. So, the output of a hidden layer ht that the RNN outputs at the time point t can be computed by this formula. WH is the weight that is multiplied with the input from the previous hidden layer, ht-1. Wx is the weight to be multiplied with the new input, xt. The lowercase b is bias. The hyperbolic tangent is the activation function. This formula seems to be complex, but if we separate these parts, we can see that it is almost the same as that of an ordinary artificial neural network. The difference is that this formula contains the past information, while in some cases, the value of ht will be output as it is. In other cases, it will be input to the next layer. We have seen a simple example of recurrent neural networks, but we can develop a more complex neural network with RNN. For example, we can stack multiple RNN layers in this way. And we can stack different kinds of layers, for example, RNNs, and fully connected layers, that is, dense layers. We can develop a more complex structure according to the problem we want to solve. No matter how many layers are stacked, the number of blocks equals the size of the sequence data. To be continued to the next session. Thank you for watching. Please thumbs up and subscribe to my channel.